Now, now in this video we will talk about ring. What is a ring? Suppose we a set of all integers from minus infinity to 0 and from 0 to positive infinity plus infinity, then integer mod n is a ring. For example, f4 is equal to 0, 1, 2, 3, f5 is equal to 0, 1, 2, 3, 4, and f6 is equal to 0, 1, 2, 3, 4, 5 are all our rings. f4 and f6 are rings. But if the number of elements in a ring are prime, that is, for example, in this one we have got 4 elements, which is not prime, but here you have got 5 elements, which is a prime number, then this is called a field. f5 is called a field, but f4 and f6 are called rings, because the number of elements in f4 and f6 are not prime. So if you have got prime number of elements in a field or in a ring, then it is called a field. So if you have got a number of elements 2, 3, 5, 7, 11 and so on, then it is called a field. Cancellation property of a ring. In elementary algebra, non-zero number a may be cancelled in the equation ax is equal to ay to yield x is equal to y. For example, you've got an equation like this, ax is equal to ay, then simply you can cancel a on both the sides, or divide the whole equation by a and you will get x is equal to y. But in case of ring, you cannot do the same. Here you can have got 2 on both the sides of the equation, but you cannot cancel these two 2's. Why? Because 2 into 5 is equal to 10, mod 6 is equal to 4, and 2 multiplied by 2 is also 4. So after doing the arithmetic operation, rather modular arithmetic operation, both are equal. But if you cancel the 2 on both the sides, then it will be 5 and it will be 2, which in that case, of course, 5 is not equal to 2. So you cannot cancel these two common factors on both the sides. When cancellation is possible, we say the ring has the cancellation property. A ring is said to have the cancellation property if AB is equal to AC or B is equal to C implies B is equal to C for any elements A, B and C. It means that if we can cancel these numbers or factors on both the sides of the equation, then we can say that the ring has got cancellation property. In this case, as in this example, the ring has got G6 has got no cancellation property. For elementary mathematics, we know that if the product of two numbers is equal to 0, say AB is equal to 0, then one of the two factors, either A or B, must be equal to 0. For this, AB is equal to 0, A must either A is 0 or B is 0. If none of them is 0, then we cannot have this A, B is equal to 0 in normal mathematics or elementary mathematics. But this is also not true in ring as well. You can get 0 without having any factor equal to 0. For example, 2 multiplied by 3 mod 6 is equal to 2 3 is 6 is equal to 0, 6 mod 6 is equal to 0, and 6 over here 6 mod 6 is also 0. So neither we don't have we have 0 over here, nor we have 0 over here, but still we get 6 mod 6 is equal to 0, even though the factors 2 and 3 both are non-zero. So such numbers, when they exist, are called divisors of zeros. When any numbers which produce 0 like this, they are called divisors of 0. In any ring, a non-zero element A is called a divisor of 0 if there is a non-zero element B in the ring such that the product AB or BA is equal to 0. Here you can see that the product 2 into 3 is equal to 0, because 2 3 into 3 is equal to 6, which is divided by 6 gives you remainder 0. Note carefully that both factors have to be non-zero. A ring has the cancellation property if it has a no divisors of zeros. So a ring can have cancellation property if and only if it has no divisors of 0. Means there is no such number where if you multiply them and take mod of that, and you will get 0 over here. If this is true, then that ring can have the cancellation property. What is integral domain? An integral domain is defined to be a commutative ring with unity having the cancellation property. If there is a ring which is commutative, means if you multiply A by B or B by A, the result remains the same, and it has got a unity or 1 as well. then it has got cancellation property, means it has got no divisors of 0. In that case, such a ring will be called integral domain. Now we will go through some basics of abstract algebra. Suppose we want to find the roots for equation x squared plus 5x plus 6 is equal to 0. By doing the simple algebraic operations, we can find that the roots of this equation are x plus 2 and x plus 3, which gives you minus 2 and minus 3 are the roots. Factors are x plus 2 and x plus 3, and roots are minus 2 and minus 3. Now we find the roots of equation 1 for mod 12. For example, the same equation is here, and we want to find the roots of this equation for mod 12. So factors remains the same, x plus 2, x plus 3 is equal to 0 mod 12. So if you have got x minus 2 mod 12, which gives you 10, x minus 3 mod 12 gives you 9. Hence x square plus 5x plus 6 congruent 0 mod 12 has two solutions, values of x10 and x9. But the thing is that in abstract algebra, this is not limited to only these two factors or these two roots. There are not only just two solutions, but you can have more than two solutions, or more than these two solutions. So what can be the other solutions? If we put 0 and place these numbers of x in the equation, and then we take mod 12 of them, then what we get is that we find that there is a solution at 1, 6, 9 and 10. 9 and 10 we already have found, but we have found two more roots, which are 1 and 6. So we can see that there are two more solutions, 1 and 6, for the equation, which we could not find by factorization. Hence, in abstract algebra, factorization is not the right method to find the solutions of the equations. So what is the main difference between this normal algebra and abstract algebra is that in abstract algebra, normal algebra, we can find these factors by just applying the normal operations of algebra, and whatever the factors we will get here will be the roots of the, or the solutions of the equation. But in case of abstract algebra, we cannot find just by factorizing the equation. We have got to put all the possible numbers, because we have put all the possible numbers because it is mod 12, so from 0 to 11, and this is the finite field. If A is a commutative ring with unity in which every non-zero element is invertible, A is called a field. Every finite integral domain is a field. A field is a set of elements on which the operations of addition and multiplication are defined. A field with finite number of elements is called a finite field, which are also known as Galois field. So as we have seen before that here, that any ring can be called a field only if the number of elements in that ring are prime. The number of elements is always a prime or power of a prime number, hence denoted by GFPM, where this P must be a prime number and this M can be any positive integer. And GFP is the set of integers from 0, 1 to P minus 1 with arithmetic operations modulo prime P. The inversion of any integer over GFP is equal to P minus 2. For example, if you want to take the inversion or A minus 1, then it will be equal to A is equal to P minus 2. We will see an example which will clarify this thing. Now suppose that f of 2 is equal to 0, 1 and f3 is equal to 0, 1, 2, then f2 is not a subset of f3. Although if you look at the elements of this f2 and f3, it seems that this f2 is subset of f3 because these 0 and 1 are common in both the sets. But this is not true in finite field. Reason is that in f2 we perform modulo 2 operation, whereas in f3 we perform modulo 3 operation, because here we have got only 2 elements, so we will perform modulo 2 operation, but in this set we have got three elements 0, 1, 2, so we'll perform modulo 3 operation. Since the operations are different, the elements of f2 and f3 are also different. For example, in f2, 1 plus 1 is equal to 0, as we know that if we have got 1 plus 1 is equal to 2, and if I take the 2 divided by 2 is equal to 0. Whereas in f3, 1 plus 1 is equal to 2. Why? Because here this 2 is present in this set, so we don't need to take any modulo or anything division. This 2 can be represented in f3, but this 2 cannot be represented in f2. So for f2, 1 plus 1 is equal to 0, whereas in f3, 1 plus 1 is equal to 2. If x plus 1 belongs to f2, then x plus 1 into x plus 1 is equal to x squared plus x plus 1 is equal to x squared plus 2x, which becomes x squared plus 1. Why? Because this 2 becomes 0. Okay, so because 2 mod 2 is equal to 0. Whereas in f3, x squared plus 2x is equal to 1. As you can see that if you are multiplying two polynomials in f2, then what the result is x squared plus 1. Whereas in f3 it is x squared plus 2x plus 1. So this is clear indication that these f2 is not a subset of f3. Now we look at the addition and multiplication of in modular arithmetic. So for example, you have got 3 plus 5 is equal to 8, then what will be the answer? Well, 1. We will simply take the mod of mod 7 of 8 and you will get 1. So in this case, as you can see the numbers, for example, this 6 plus 6 is equal to 12, and then if you take mod 7 of 12, then you will get 5. 4 minus 6 is equal to 4 plus minus 6, which is equal to 4 plus 1, which is by 7. Simply subtract this 6 minus 6 from 7, and you will get 4 plus 1, which is equal to 5. 4 multiplied by 4 is equal to 16, mod 7 is equal to 2. In this modular arithmetic, we don't have division. So for division, we also perform the multiplication. 4 divided by 5 will be written as 4 multiplied by 5 minus 1, because it is 5 will be inverse of 5 will be multiplied by 4. And as we seen before, I told you that any inverse is equal to p minus 2. So in this case, our p is 7. So 7 minus 2 is equal to 4 multiplied by 5 is to power 7 minus 2 is equal to 4 multiplied by 5 is to power 5, because 7 minus 2 is equal to 5. You simply multiply 5 times and you get 4 multiplied by 3, 1, 2, 5 mod 7. And if you take mod of 3, 1, 2, 5, you get 3. And then again, if you take the mod of 4 into 3, then you get 5. So the answer of 4 divided by 5 is equal to 5. Properties of binary Galois field. We consider only binary field GF2 and its extension GF2 prime, where m belongs to 2, 3, and 4. M can be any positive integer greater than 1, or it should not be 0. The following is always valid for all numbers in Galois field. Fields contain 0 or 1. Adding, subtracting, multiplying, or division gives one of the numbers in the set. Of course, this is the main property of the field. Division by 0 is not allowed. And addition in finite field is equivalent to logic exclusive XOR or XOR operation. And multiplication in a finite field is equivalent to logical AND. Now we will do this example of calculation of GF7 in the next video.